The energy density gives us another way of understanding the elasticity. There's an energy for each bond, U, and there's a density of bonds, or an inverse of a length cubed. So the elasticity can be written as the energy of the bond divided by the length between the bonds cubed. That's an energy density. And that's a good way of understanding the origin, the physical origin of what the elasticity is. It's basically the amount of energy it takes to deform all the bonds. Because when you're changing the dimensions of the food, when you're changing the dimensions of an object, which is what you have to do, when you measure the elasticity, you have to deform all the bonds, then it's just a measure of the energy density, how much the energy of the bonds are and how many bonds there are per unit volume. So you can understand elasticity not as how you deform the food, but how you change the length of the bonds. You need to know the energy of the bonds and their density, and that gives you the origin of the elasticity. So let's measure the elasticity of this steak. We'll start with this rare state. We're going to do that in the same way, using the same equation that we used for food, which is like Hooke's law, which is the stress divided by the strain. So what we'll do is we'll take a piece of steak, we'll cut it in a known dimension like this. Here's the dimension of it. The height of the steak is 20 millimeters, 2 centimeters, and we have an area. We just calculate the area. It's 16 square centimeters, 4 by 4 centimeters. We have this cube of steak, and we're going to deform it by putting a weight on top of it. So let's do this. We'll deform it. The weight that we're going to use is 200 grams, or 0.2 kilograms. And let's measure the deformation. Remember, the original height of the steak is 20 millimeters, 2 centimeters. So let's put the weight on top of it. We measure the deformation, and it gets thinner. The length, the height of the steak decreases by 5 millimeters. So we have a deformation of 5 millimeters out of an initial value of 20 millimeters. And we have a weight that is a mass of 0.2 kilograms, 200 grams. So if we want to calculate the force, we calculate the force as just the mass times the gravitational acceleration of gravity. That's 10 meters per second squared. And so the total force is 2 newtons. And we have 2 newtons, and the strain is 0.5 centimeters divided by 2 centimeters. And when we calculate this, we get a value of 22,000 pascals, or 22 kilopascals. Now we can do the same thing for this well-done steak. We've cooked it longer. We can take the piece. It's the same dimensions. We'll cut this cube into exactly the same dimensions. But now, in order to get a measurable deformation, we have to use a larger weight. We have to use a mass of 1 kilogram. So in this case, the total force is a mass of 1 kilogram times the gravitational acceleration. That's 10 newtons. The total force is 10 newtons. The deformation in this case, we start again with a cube whose height is 2 centimeters or 20 millimeters, and it is deformed in this case only by 2 millimeters. Much smaller deformation for a larger weight. The steak is much stiffer now that it's cooked. If we do the calculation, in this case, we find that the elasticity of the steak has increased. It's now about 63,000 pascals, or 63 kilopascals. So the elasticity of the steak has increased by about a factor of 3 as we cook it. What's the origin of this? It's a combination of the fact that some of the bonds may change their energy, but most likely the number of bonds have increased. You form new bonds, so the density of bonds has gone up. There are more bonds per unit volume, and that leads to an increase in the elasticity of the steak. So the elasticity of a well-done steak is much larger, it's much stiffer, it takes more force to chew it. It's more difficult to chew the well-done steak. That's why it's related to the mouthfeel, to how it feels in your mouth. So when we chew on the steak, when we bite the steak, we can deform it just a bit, the same way we did when we made our measurement of the elasticity. We just bite just a little bit into the steak, and we squeeze it, we deform it, we make it less thick. But really, when we chew on it, we don't want to just deform the steak. That tells us how the mouthfeel is. That tells us how it feels in your mouth. But in the end, we want to chew it. We want to break it into much smaller bits. And so when we bite really hard, we actually cause it to break or yield. And so there's another characteristic value of the steak or of any material, and that's called the yield stress. What is the force or the stress that you have to apply in order to break the food, to make it completely come apart? Again, this depends on the nature of the food, but typically the yield stress is proportional to the elastic modulus. So if you have something that's much stiffer, you have to apply a larger force or a larger stress to make it yield, to break it, to chew it. So the yield stress, when you have a steak that's well done, is much larger than a steak that's not so well done, that's rare. The elastic modulus is larger, and so too is the yield stress. Another way of understanding it is very often it's not the yield stress that tells you when it breaks, but it's the strain. You have to deform it a certain amount. If you have to deform it the same amount, whether it's a stiff material or a softer material, then the yield stress also varies just with the elasticity. You deform it the same amount, so something that's a stiffer material that has a higher elastic constant will also have a higher yield stress. Something that's a softer material, has a lower elastic constant, will have a lower yield stress.